In terms of looking at the specific K, when we talk about salts dissolving, it's called the solubility product constant. And we abbreviate this as KSP. This is the entire focus of lab number 1. It's a 2-lab period lab. And the solubility product constant is the constant established for the equilibrium between a solid solute and its ions in a saturated solution. The key thing here is our solution needs to be saturated. And the first part of experiment number 1, what you did was you had to form this saturated solution. Sometimes it's not that easy to make a saturated solution of some of these, complexes that we're going to analyze. You took a certain amount of, solid. In this case, it was calcium iodate. You dumped it in a beaker. You had to stir that beaker up for a while. And then you tried to form a saturated solution. You're going to see, and after you're done with your experiment, you're going to calculate a KSP value. One of the things that we don't get to emphasize as much in the earlier chemistry courses that we can right now, and I will say this till I'm blue in the face, chemistry is an experimental science where measurements are made. Anytime you now look at a KSP value, we're going to give you tables, right? If you look in your lab manual, there is a table of KSP values. These values aren't randomly generated. They're not just numbers. They are data that have been collected very, very carefully in a lab. It takes you roughly 6 hours to generate the KSP value for calcium iodate. We have an entire table with 50 KSP values. They've been generated and refined over time. So whenever you look at a value like a KSP, don't think of it as just a number. Think of it as a process, and think of it as a solid dissolving into ions in solution. So one of the things that I really want to emphasize is that all data collected in KSP tables is experimentally determined. This is the same for pretty much any type of data that you'll see in a table in a textbook. We have to go into the lab, we have to perform an experiment, that experiment needs to be repeated, and then we come up with a particular value for that. So what we did is we're going to experimentally determine the KSP for the following expression. In our case, we have calcium iodate, which is CaIO3 twice, as a solid in equilibrium with calcium 2 plus in aqueous solution plus 2 IO3 minus also in aqueous solution. From this, we can write a KSP expression. When we write any type of K, it's going to be the concentration of the products divided by the concentration of the reactants. So when we write a KSP expression, the products are going to be the concentration of calcium 2 plus times the concentration of IO3 minus, that quantity squared. And in a K expression, we need to use the coefficients as the exponents in our expression. One of the things that we can say is that if you have a pure solid, a pure liquid, and a solvent, these guys do not appear in the equilibrium expression. So in this case, we have the calcium iodate as a solid, but that's not going to show up in here, so our KSP is going to be the concentration of the calcium 2 plus times the concentration of IO3 minus divided by 1. So all of our KSP expressions are going to look like this, because if we're looking at a KSP, we're talking about a solid dissolving into ions. So this is how the chemists set this up, and this is the notation and the convention that we must use. So one of these things that we can say is the KSP is a measure of how much solid dissolves to form a saturated solution. Notice I keep saying the saturated solution part. KSP is an equilibrium constant, and at equilibrium, our solution is going to be saturated. That's what we're defining as our equilibrium point. So what we can look at is various measures of solubility. If you're, maybe in 7th or 8th grade, typically when we talk about solubility, we don't introduce KSP to 8th graders, at least not in most cases. You could be a little Einstein running around. But in most cases, we say that solubility is defined as a grams of solid that dissolve per liter, or by some kind of particular volume. If you're a diligent high schooler, you can go from grams of solid dissolving in liters to something that we can say is molar solubility. So we can convert grams to moles, and we can get a molar solubility. From that molar solubility, we can convert and get a KSP value. And in reality, we can interconvert between all of these quantities right here. One thing that I want to note, that the KSP is not a measure of solubility. It gives us an indication of what the solubility is, but if I asked you to rank a set of compounds in order of their solubility, do not put them in order of their KSPs. There's a certain exception to that I'm going to go over here in a second, but in terms of solubility, KSP can allow us to calculate the solubility, but just a fixed KSP value will not give us solubility in order. We have to investigate these in a little bit deeper sense. So one of the things that I want to look at is an example of this.